with Junchen Rong. Yes. You will teach us how to go to the sun?
Yes. So if you remember Martin's talk on Monday, he was talking about how to navigate outer space. So I decided to continue that journey and explain how to go to the sun. This is a joke I borrowed from Eliezer Romanovich. And the actual thing I'm going to talk about is how spontaneous breaking of finite group symmetries at all temperature. So we are going to talk about a state of matter, which is some ordered phase, spontaneous breaking of certain symmetry, which usually these kind of phases would stay at low temperature. But the system that we are going to discuss will be in order phase, and this order phase will persist until like really, really high temperature. So if you think about it, suppose we have a material that persists, that does not disintegrate until infinite temperature. We can use it to do some spaceship and go to the sun. That's the logic behind that joke. But let's start with some quantity transition that is familiar to matter physicists and probably most of us. Let's consider transverse field Ising model. So the Hamiltonian would be like this. Summation over Ig with nearest neighbor pairs, Zi. This is a Hamiltonian Z, and X here are the polymatrices that we are familiar with. So this guy has a global Z2 symmetry, and it's easy to show that this operator, this means the tensor product of the X matrix of all the spins, all the lattice sites. If you check it, you would easily see that this guy commutes with your Hamiltonian, because this is the X polymatrix. They easily commutes with this guy. And because it's a tensor product of at least two, therefore this each of these zi's anti-commute with xi give you a minus sign, but this is two zi's, so they give you a plus. So this system is a Hamiltonian. So as you tune this coupling constant h, it will have some phase transition structure. So the easiest to see it is let's see, when h is much bigger than g. And we can essentially neglect the first term, and this polymetric is playing the role. So we are basically in this state. I'm denoting this as the spin is inclined to pointing towards the x direction. And it will be a superposition of this upper spin state minus I lower spin state. Okay. And since it's a mixture of upper and lower spin, and it has a unit amplitude for each of the states, if you measure the expectation value of your Z, let's see, I, you will get 0. So in terms of Ising model, this means the system is in a disordered phase and your symmetry is not broken. On the other hand, when your H is much smaller than G, you should essentially neglect this second term. The first term prefers your spin to be along the same direction, each of the spins along the same direction. So therefore, this is the state where the spins is broken, the Z2 symmetry is broken. So let's draw some phase diagram here. So this is H over G, and there's a critical H critical over G. And in this phase will be the disordered. Okay. And this phase would be the ordered phase. So our discussion will involve temperature. Suppose you don't really have this H term, you are basically treating a statistical physics model, which is the Ising model we are familiar with. So we know at low temperature, this guy will be in the ordered phase, as it's shown here. But we also know at some critical temperature there will be some Tc over G, and above which the system goes into the disordered phase. So in reality, what the phase diagram looks like is this. You will have a line that connects this, and your ordered phase is constrained in this subregion of your phase diagram. Okay. There are a few things to be mentioned here. One thing is that if you look at what's happening here, at high temperature, this V2 symmetry always gets restored. That's actually is how do you see? Is consistent with what we expect from thermodynamics, because high temperature usually we want the system to be more and more disordered. The second thing is that this is the 2+1 dimensional Ising model, which is the critical CFT, it's a CFT fixed point. So you can see, so basically what's happening along this line is described by your CFT putting on finite temperature, which will become more clear later. So today we are going to look at systems with a more exotic phase diagram. Basically, this axis would still be my temperature, and this axis would be some, let's see, some coupling of relevant operator, such like some S terms. Okay, and our phase, we will still have a quantum critical point here, the quantum CFT point, but our phase diagram would look like this. And this is in the ordered phase. This is in the disordered phase. Okay. It's exotic in two things. First of all, if you look at what's happening here, the phase diagram is inverted. At low temperature, it's in disordered phase, but at high temperature, it's in the ordered phase. So it's kind of in contradiction with our expectations of thermodynamics. The second thing is that, so along this line, your CFT at finite temperature is given by ordered phase. So for those who are familiar with finite temperature bootstrap, I would say that if you solve the bootstrap equation, you should find two solutions. One solution is the solution that basically your operator, you don't have symmetry break-in. Another solution is the solution with symmetry break-in. So let's see a bit more about it. So if your system is at finite temperature, you can have 1 point expectation values because your system has a scale. The scale is the inverse temperature, or so therefore your operators can have, let's see, some AO and beta to the, sorry, it should be 1 over beta to the delta O, or simply AO T to the delta O. And this A is some dynamical information of your system. This is kinematics, because it's fixed for you the power law dependence of your temperature. But here it's some dynamical numbers you are supposed to solve using your field theory methods. So by saying this line, I basically means that my operator carries some indices. And these indices would be an index that belongs to a representation of some group. So by making this guy have an expectation value, my symmetry would be something is broken. It would be it will break some symmetry of the system. Okay.
Sorry, why should there be two solutions? In that phase diagram, it looks like to restore the symmetry, to go to zero temperature.
Yes, but the same set of CFT data, it will have two solutions. One is unstable. So basically, when we solve for we are not going to use Bootstrap to solve it. We are going to solve for the thermal mass, effective thermal mass. If you have solve it, you will see that this small mass has a negative direction. And that means, okay, there is an unstable solution at the origin, but also there is a direction that you would pick, which is a stable solution.
Right. So, but this is a feature of the model, or it's just it's going to be a feature of the performance Bootstrap at finite temperature.
It's a feature of the model. In your case, you would see this, basically. This is in the disorder phase, so your thermal mass would be positive. And your original vacuum would still be stable.
Yeah, sorry, I just not what I meant. So if I have a CFT which has the second phase diagram,
Yeah.
will there always be also a solution with an unstable solution with no symmetry breaking?
Yeah.
In any CFT which has this feature, it's not a perturbative like a Lampos effect, like the models you can write have this potential.
Yes, I believe so.
Okay.
Yeah.
So indeed, there might be a possibility that this second solution just doesn't exist, that if you try to solve carefully, there's only one solution. Because CFT is a non-perturbative framework, it should not give you some
Yes, so I would take that as,
solution.
yeah, I would take that as a challenge for fine temperature bootstrap people. If you if you were able to show it, it would be really nice. What the calculation I'm going to do is basically still perturbative. So yeah.
So your operator, when it gets this one-point function, presumably, I would guess that the one-point function would like explicitly break the symmetry, like the values AO. Would not respect the symmetry. That's what you mean?
Yes, yes. I'm basically meaning that my O, for example, suppose this is the vector representation of ON, and this guy has the expectation value, basically means that you are breaking the symmetry.
Well, I mean,
It's just like Euro spontaneous breaking of symmetry, right? Of ON vector model. Sorry.
like if it was, if this value respected the symmetry still, if all the components had the same would that still break?
It will be the same for all. I mean, so basically your potential looks like this, and there will be a circle. So this guy, as you change this rotational direction, it's a constant. So basically, what I'm saying is that it's like a Mexican hat potential. You pick your vacuum would be your system would pick a specific vacuum at some point. And the other component would not be. So yeah. So it's not constant around the circle. It picks one direction. Yeah.
You define orders to be the state with a non-zero valve.
The state with a non-zero valve, but also carries a flavor symmetry index. The operator of a certain flavor symmetry group, the representation, it carries non-trivial representation of that flavor symmetry group, and it has a vacuum extent.
Okay, because this is the state that if the phase diagram is inverted, it must be the state with higher entropy. So it's a bit odd to call it ordered.
Yes, but we are talking about CFT, so CFT are, I don't know whether we should think about some of that in terms of CFT. The story all started with a remarkable work by Weinberger, which is on PRD. Volume 9, 1974, 3357. Okay, so he considered a scalar theory, which is very easy to write down. If you turn on finite temperature and your temporal circle is basically your finite radius, and if you are looking at the scale of physics at the larger scale than this radius, what you can do is basically a closed line reduction on this summer circle, and each of these closed line modes would just be the most barren modes. And therefore we can basically put an andaz here, our phi to be exponential I 2 pi n tau divided by beta. Tau is your imaginary time direction, and you can put a phi n of x here, and this x would be your three spatial directions. This is, sorry, I should say this is 3 plus 1d, And if you do the compactification of your one-time direction, you would get a three-dimensional Lagrange. So basically, your action becomes 1/2 phi 0 plus lambda beta minus 1 all factorial phi 0 to the first plus a kinetic term for your Masbara modes. Okay, so we essentially plug this anzacs into this action, and you would reach this mode. So first of all, there's a zero mode, which is massless. There's also a higher Masbara frequency, which is massive. The mass is given by this formula. Okay? And there is an important term, which is the interaction between the free mode, the zero mode, and the higher Masbara frequency. So there are other terms, but we are doing one loop calculation, so the other terms will not play a role for our calculation. For example, there would be four point quadratic terms for this higher mode, but that's second loop, so we will not pay much attention to it.
So you are tuning the mass to 0.
Yes, I'm tuning the mass to 0 for the moment. Okay, maybe I should add it. So the diagrams is very easy, it's just one loop diagrams. We are going to consider the diagram like this. What's propagating here are the massive modes. What's here is the zero modes. So this loop would just renormalize your mass at finite temperature. So the calculation is also very easy. So your sum of mass squared would just be essentially lambda beta minus 1, which is this coupling here. 1/2, and there should be a summation from n equal to 1 to infinity of your loop diagrams. Okay. And this integral is can be performed analytically. It has been known for many years. That actually, let me write it down for simplicity, for explanation. D is equal to m squared d minus 2 minus 1, d over 2 minus 1, 4 pi d over 2, gamma function y minus d over 2. Okay? In generic dimensions, it's known. And therefore, you can simply plug it back in here, perform this integral, and your sum of mass essentially becomes negative 1/2 beta minus 2 lambda summation n from 1 to infinity, which n. And you can use this function to regularize it. And what you are getting is lambda over 24 beta minus 2. Okay. So, okay, I erased my phase diagram. Okay, so let's postpone that to later. So this is basically, as you turn on temperature, what your mass looks like. So you can see it's a positive number for a single scalar. So the models that we are going to discuss will be a bit more complicated. So therefore, it would be interesting to know what's the generic formula for this small mass. So let's just simply consider a potential, which looks like 1 over 4 factorial, lambda I, g, k, l, phi I, phi g, phi k, phi l. Okay? It's the most generic potential you can write down for lambda particle theory. And you don't really need to do much calculation. First of all, your diagrams looks like this. And from the group structure, you can easily know that it has to be proportional to this guy, right? Because you have to do summation over the loops. Chi is assumed to be summed. Also, because of dimensional analysis, you know it has to be proportional to -2, weighted to -2. And also, you want to go back to the single scalar case, and therefore you can fix this proportional constant immediately. That gives you a 24.
Sorry. So here you use the specific regularization scheme, which means that you had a counter term somewhere, which is divergent. So
Yes, yes.
so the fact that this is positive depends on what is the mass you started from. I mean, there's
This mass are the Masbara frequency mass. So what that counter term does is to renormalize the counter term is this term. So
Yeah.
so I mean, but we are going to talk about the safety point. Basically, we tune this to 0 at that point. So that counter term. What's really important is this dependence onto t squared. So yeah. So it's a specific regularization, but that given dependence is only in this piece.
It will look like I need to tune it once to reach the safety point, and then I need to tune it another time to get the positive result you got there. So I'm a bit confused at which point are we tuning m squared. I mean, if I start on a lattice system which has some lattice spacing, so I don't tune anything, I can tune the temperature or whatever, this coefficient to reach the CFT point, then I put it at finite temperature, saying the thermal square at that point comes out positive in this model. But since you use a regularization scheme there, it doesn't look wrong.
I think you just tune it once at 0 temperature. You fix the counter term, and then you're done, right?
But then why would that give that specific regularization for the zeta function?
The loop diagram is present at 0 temperature, and the divergence comes from high momentum region, which is exactly the large N region in the sun. So
Okay.
it's
Yeah.
divergence.
It's the same, right?
Okay, that's a more clear explanation. Thank you. Yeah. So
So you're saying a counter term, you have lambda squares, if you have a momentum cut, or
Yeah, you could use DimRad in flat space, compute all the counterterms, and if you did that, the counterterm would exactly cancel the.
yeah, but DimRad doesn't give you the power law, that doesn't show you the two rooms. So I want to say that there's a quadratic divergence, which would be cut of squared, lambda squared, and then there's a thermal mass, which is beta to the -2. And I guess the statement that Marco's after is that there's no divergence of the form lambda beta inverse,
yeah.
right?
So
Which is not
yeah,
entirely obvious here.
basically beta -2 coefficient is regular. It has no cutoff dependence.
It's not entirely obvious to me because you have something that's a beta inverse and it's linearly divergent at large scale. So that's why I'd like to do just the first year graduate computation where you just said do the momentum cutoff and see that there's no lambda beta inverse.
Well, in principle, you can.
Right, it's a bit like an IRUB mixing, but since you're doing Kaluza-Klein reduction, because lambda is a 3D cutoff and beta is an IR system size, but because you're mixing modes, you do this KK reduction. I'm not entirely sure that term does not exist. And that term would imply the tuning that Marco is talking about, so the thermal mass.
It would have to go away if you use the Lorentz invariant regulator.
No, I think maybe.
Yeah, because the whole point is that the large N region of the sun is like a momentum integral.
Well, I mean,
I'm talking about large K, for example.
If the time reassure you can do the work calculation in constant space, where it's clear that the difference between finite temperature and back loop is finite temperature.
Clear that the difference?
The difference is unambiguous. The difference between the finite temperature loop and the zero temperature loop is unambiguous and it's finite.
But this is the zero KK mode, so, okay, I guess it makes sense. Right, the zero KK reduction, so you're rewriting your field 2 degrees of freedom.
I think Simone is just saying you can write that integral and you can write the corresponding integral at 0 temperature, and you can look at the difference and you can see that it's not divergent.
Yeah, if that's a little more clear. I mean, you can put a tangent here and deform your contours and really show that there is a divergent piece at 0 temperature. And the second derivative over temperature, which gives you this, would be lambda over 24.
Perhaps. I mean, I just see a linear divergence for large K there. Fix it.
Yeah, can we put it aside for the moment?
That goes to the heart of what we're trying to discuss. Sure.
The question is really about what schemes to use, not about just getting an answer. But I would have thought it's more natural to just do the sum over n first inside the integrand.
Yeah, that, you can put a tangent here and deform the
Why do you
contour.
just put a tangent? You just evaluate the integrand directly. It is a conversion sum over n, and then you do whatever regularization k you want with the cutoff. Fine.
It's not putting a sentence, I'm just saying that the sum is a tangent. Sum over n.
It's the same thing. And, okay, let me continue, and I'm pretty sure that's so you can what Wimmer did was this. So to pick a potential like this, lambda 1 1, lambda 1 2, which plus lambda 2 2. Square. So this potential, this vector means it's an n-dimensional vector. So what I'm seeing here is I'm talking about potential that preserves On times On symmetry. The phi 1 would be in the vector representation of the first On, and phi 2 would be in the vector representation of the second On. And you are basically, okay, this term is On invariant, is On invariant. You have two systems that you couple them through their mass terms. Okay? And you can basically plug this into the system, and you would find your sum of mass. Now, two eigenvalues, because it has to be proportional to the quartic invariance. So we have basically phi 1 and phi 2 would have two different sum of masses. And your first one, called 1, is going to be this value, 1/3 n plus 2. Okay, so you need to satisfy a few conditions. First of all, you need the potential to be bounded. Therefore, lambda 1 1 needs to be bigger than 0. Lambda 1 2 needs to be bigger than 0. You want a negative sum of mass, so you would need lambda 2 2 needs to be bigger than 0. You need a negative sum of mass, so you need a negative term here. So your lambda 1 2 needs to be less than 0. In the meantime, if this is the case for the potential to be bounded, you also need the lambda 1 2 square to be bigger than lambda 1 1, lambda 1 2. These conditions, less than. Also, you want this guy to be much larger than the other one. So, for example, lambda 1 2 is much larger than Okay, these are the conditions that you need to satisfy to have
You mean
inverted.
You mean lambda 2 there?
Yes.
Do you mean 1/3?
Why much larger?
Well, you want, well, maybe not much larger. Okay, sorry. Absolute value of this guy would be much larger.
But why much? The width is much.
Not necessarily much, that's true. A little bit large. That's larger. Yes, so,
Sorry, could you explain why you needed to go to a theory with two masses now? Because you started with an example with one mass.
yes, I will explain that later when we comes to CFT, which would be much cleaner. But yeah, basically when we tried and didn't find an example with just one mass. So. Then these conditions, what we showed is that, okay, you can go to a perturbative limit. Basically all these conditions can be satisfied with the condition that lambda 1, 1, lambda 1, 2, and lambda 2, 2 will be much less than lambda 1. Okay? So you remain the perturbative limit, and your one loop calculation is trustworthy, and you would get an active thermal mass, and you would have inverted phase-time. Go ahead.
Are these conditions consistent with the potential being bound from below?
Yes, so this and this is making sure that your potential is bounded at infinity.
Or both? Okay.
Yeah. So
Sorry, I missed another point. Do we need one or both of the thermal masses to go?
we can only make one with them to be active. So yeah, that's what we did. So you would have a phase diagram looks like this, and this will be ordered phase, and this will be this will be disordered, and this will be some ordered phase in here. But this is perturbative, right? So perturbatively, when you go to higher temperature, go ahead.
You need to tune two masses, right, at zero temperature.
Yes, you need to tune. Actually, you need to. When I talk about my safety, you would realize immediately we need to tune 3 operators, which is a bit much.
What 3 operators?
Yeah, there's another one coming from the stability matrix of the beta function. When I talk about safety, but yes, now you need to tune 2 masses.
Why don't you impose just the two invariants between these two ends and then you only need to choose one mass?
Yeah.
In that
No, I don't. I can't because I need my. No, yeah.
So if you set lambda 1, 1 equal lambda 2, 2, you can still satisfy.
Yes, there's no condition that stops you from doing it.
Yes, you can't, because the Hessian condition would be in conflict with the lambda 1, 2, 3.
Sorry, which one?
You need lambda 1, 1 to be different from lambda 1, 2, 2. Otherwise, the Hessian, the top right condition will be in conflict with the condition of x line.
Mm-hmm. Yes.
So if you impose this Z2, you need lambda 1, 1 to be the same as lambda 2, 2, right?
Yeah, then you would be a single representation of O1 times OM of Z2. I think for a single representation, it's not possible. I don't see it immediately, but you need to have 2 representations of some groups, so that you need to, yeah. So basically, what we did is a perturbative calculation, and you don't really know if your temperature is like very, very high, what would happen. So whether this will be restored again or something. So, but
Sorry, so what's the symmetry of this model?
it's going to be OM times ON. This phi 1 is in the vector representation of OM, the first O. Oh, sorry, ON times ON. This vector will be the first representation of O. This ON, this guy will be the vector representation of the second O. So, but before we talk about CFT, let me mention there really is a material that does this. It's called Rochelle salt, and it's a very popular material that YouTubers are making videos. Okay. So there are a few transitions. Okay, this is 0 degree. This is negative 18 degree. This is 24 degree. And there's a 55 degree. Well, it's just room temperature. Therefore, you understand why YouTubers like it. And it has a few different crystal structures. First of all, about 55 degrees, this is liquid. It will just melt. And here is called, I'll just write it down because I don't know how to pronounce it. Although, how maybe? Say it again?
I think you're missing the letter there. Like an R?
Yeah, that's an R. Okay, so basically, the basic thing I want to see is that this guy has a higher symmetry. This guy has lower symmetry. This guy has higher symmetry. Okay, so you can see the phase transition negative 18 degree is having an inverted phase time. That's like what Wendell described. But this ON times ON models is under debate for many years, and it's still not too much clear whether this perturbative calculation is really happening or not when you build lattice models or analyze it using other methods.
Sorry, but what does it do, this material, to be so funny for YouTubers? What do we see in the transition?
I don't know, actually.
In your formula for the thermal masses, it should be the same prefactor for both 1 and 2, right? You have a third and a half.
Yes, sorry, this is master. Typo, thank you. Right, so this result was sitting there for many years, and basically a few years ago, 2 or 3 years ago, there was a paper by Chai, Chanduri, Choi, Rohakon Glosky, Eliezer Robinovich, and Michael Smolin. I won't write it down because too many. But the insight from this interesting paper is that you need to work with CFT. Okay, if you work with CFT, I already explained that your one-point function, you just have one scale in your system, and therefore, if your one-point function has a broken face, it will persist until infinite time. So we already wrote down our sum of mass, which is 4. And we need to perturbatively, we need another condition, which is basically the beta function d equal to 0, right? So we are going to do a 4 minus epsilon expansion. You are going to have a beta function which gives you 0. You need it to be 0. So basically we need to satisfy these two conditions. Okay. Now it's a purely mathematical problem. purely group theoretical, well, not mathematical problem. Let's look at, again, the Ising phase diagram, and try to understand it. If you just pick this lambda to be the Ising model, just a single coupling constant, you would be able to solve this with a point, right? And you plug it in, you will notice that your sum mass would be proportional to this coupling constant, which is order epsilon. And so let's look at our phase diagram and try to understand what's the physics here. This is your quantum critical point. This is your edge coupling. This is your temperature. So let's look at this history, right? Suppose I tune my my mass, my coupling to be slightly away from the critical point, and therefore my theory would already have a negative mass squared. I tune my mass to be some negative number, and I would have another contribution which is coming from the thermal contribution, which would be some number t squared, right? This is the thermal contribution. Together, it gives me my so-called my effective products. So solve this, you would get the critical temperature, and it will depend on the original mass square. Basically, it's the distance you are away from your critical point. So therefore, you notice that your TC would be some square root of your m squared. Maybe I would call it h minus hc, just in case. Okay. And you can see this is the square root of behavior that is happening here.
Sorry?
Sorry?
I'm a bit confused. Is that the beta function or the temperature depending on the coupling lambda?
Apologize for using two beta letters. This is the beta function. This is the inverse temperature. Yeah. So this curve would be a square root behavior, which would be, if you are taking into account of the actual renormalization, it will be some critical exponent, basically relating to the scaling dimension of the epsilon operator. Right? So. Okay, so first of all, as I promised, I need to explain why a single representation is not working. Basically, if your group has a single quadratic invariant, it will not working. Let's scale our lambda a little bit. Let's just erase this epsilon. I should put a hat there, but okay, I should also renormalize this constant, but let me just call it tutor to be 0. Okay, so let's change the sign here. And if you have a single representation, let me change this L index, close it to be k and summation over k. And the condition we need to satisfy is lambda ijkk tutor equal to lambda igmn lambda mnk k plus 2 lambda tutor igmn lambda tutor mng k. Okay. Sorry, IK. Okay. And if I have only one quadratic invariant, this guy needs to be proportional to that IG. So I would just see that lambda IGKK, this K summation, would be proportional to a single constant of the IG. You can just plug it back in, okay, and what you are getting would be Z third IG equal to z squared, delta ig here, and this piece. This piece is positive definite, okay? And this piece is z squared, so it's positive. So therefore your z is positive. So that's why I'm saying that a single representation is not doing the real. It cannot be it. So that's why you have to go to two representations, a series with two mass operators. Basically, that's a little bit bad news because in the experiment you need to tune two parameters. Yeah. So what that paper did was to consider basically Weinberg's model in finite epsilon. It turns out that ON times ON model that I explained, I wrote down a little bit earlier. It turns out this is not working. There's no fixed point with negative some raw mass. What you need to do is to go to OM times ON, and you have to choose M and N to be different, and you will find particular fixed point.
So what was wrong with what you explained, this computation by Weinberg?
It's perturbative. We want to, it's nothing wrong. It's just it's perturbative, and we want a high temperature.
I think if you also check the beta function, it doesn't work.
No, Weinberger needs to tune the lambda 5 for couplings. He's in a near a free series, so you would be able to tune it, at least theoretically, you could be able to tune it. But if we are at a beta function, our couplings are constrained by these conditions. We have to fix it.
You add this condition, but then it doesn't.
Yes, and therefore you don't have the freedom of tuning your lambda 5 for couplings. So you want a different groups. That's what that Lam paper did. Basically, yeah, as I explained, that the insight is to go to CFD, and CFD helps us to fix the infinite temperature here.
Question?
Sure.
In 3+1D, does Weinberg's does ON cross ON work? If you consider
OM times ON.
Yeah, if you consider the logarithm.
I mean, if ON times ON already works, if you are able to tune the complement.
No, you didn't take into account the logarithmic flow, right?
Did I take into account the logarithmic flow? Yes, I didn't. Yeah, so I guess what you mean is that another problem of this lambda 5/4 is that there's cutoff, right? There's it's not UV completed. So
I don't care about UV. I always have a lattice, but but one does need to take into account the beta function even in 3+1D.
Right, but I don't think you would have a fixed point if you do that. Well, this is related to another approach people are using. There's another approach, orthogonal to finite epsilon, is that people are using Banzaks-like fixed points in QCD to create a fixed point, a safety point. But if you start with scalar series, I don't think there's a safety nearby.
Sorry, but are you just to understand it? Are you saying that you will have lambda evaluated at the scale theta, for instance, which is not zero?
At the scale of the temperature.
I see. I don't know actually. That should be an interesting problem. Yeah. So let me continue. These are finite epsilon results, and these are very good models. But there is a point that you need to improve. It's basically when you take epsilon go to 1. If you think about it, think about our Friis diagram. This is the critical point. This is some Raman coupling, let's call it H. This is temperature, and we want Friis diagram to like this. This is disordered. This is ordered. But as I just told you, if I turn on temperature in this region, my system would be a two-dimensional system. because I take epsilon to be 1, therefore my CFT is a 2 plus 1 dimensional CFT. Okay, it's a 2 plus 1D CFT. If I turn on temperature, it becomes a 2-dimensional system. Okay, and there's a famous theorem. I'm going to list all the names because Coleman, I guess we all know which theorem I'm talking about. Wagner basically tells us that cannot be continuous symmetry breaking phase in 2 dimensions, right? So therefore, the non-perturbative effect, as I was mentioning, has to be somehow kick in and destroy this ordered phase. So, strictly speaking, this model works only in fractional dimensions. So that's we did a little bit more step. Basically, to bypass that, you consider finite groups. That's why where the title is. So there are a few famous CFTs in format safe zone, and I'm pretty sure it also exists in 3D. One is the cubic fixed point, number 54. Another is, I think, is named tetrahedron fixed point. And there was another one, but I'll just talk about these two. The cubic one is a Lagrangian like this.
Excuse me, another question about this. So the fact that you can apply the theorem is because if you are at the critical point, if you were in infinite space, the two-dimensional theory could be non-local, so this theorem may not apply. But you're saying since it's a circle, the 2D is local.
Your original theory is local. We have partials. We have.
But
after close to 9, it's still local.
Yeah, but I don't. If I restrict to 2D, 3D theory, it doesn't have stress tensor the 2D theory.
Yeah, if you actually, I said there is one approach where people were trying to build to bypass this theorem, is to work with 3 plus 1D Banzak's type of fixed point. That's the approach by. Okay, I will mention the names later. There's another approach which is to work directly in 2 plus 1D in 3D. And you'd consider long-range models, and that model indeed, if you start with that, you would be able to bypass this theorem because long-range models do not have Gaussian models basically. Okay. So we are conservative person, so we still stay with short-range models, and your cubic Hamiltonian is. Same thing. Okay, in case you are not familiar with it, this is the term that preserves the ON symmetry. This is an anisotropic term which breaks the ON group into a subgroup of ON, which is called the cubic group. And the symmetry of this guy is usually written as Sn, weird product, because it's not direct product to the nth power. So what does this Z2 do? Each of this Z2 flips one copies of these scalar fields, right? Flips the sign of the one copies of these scalar fields. And Sn is basically the permutation around the different copies of this. So I should write here that I goes to 1 to n. Okay? And I will have a second one. I'll just write it as phi 2 hat.
Why is the product funny? Why not just use it?
Because it's not direct product.
Why is not direct product? Why can't I just click?
Sorry.
to me it looks like Sn is a symmetry and Z2 to the n is also a symmetry. It's like
Yeah, it's a symmetry, but it's not direct product.
why? Why can't I just do just
It does not well, the Sn commutation and the Sn permutation and the Z2 are not commute with each other. That's I could write cross here, but it's not commuting the permutations. If I flip copy one permutation, I would be flipping a different copy. So it's not commuting. Okay, so I would just write it a second copy, which I call it phi 2. It's the same Lagrangian, but with a 2. It's the second copy of cubic. And I need an interaction term, which for interaction to be simply, okay, maybe I should write my couplings. I'll just have a lambda 3 term, which is a nullity of this guy. Something plus lambda 3, some terms, plus lambda 4, of some terms. I'll have an interaction term, which I'll call it the fifth coupling. This guy, okay? Now I have 5 couplings. I don't really need to explain to you how to do the calculations. Basically, it's 2 equations. You plug in, you check, and it works. So, yeah. So if you check it, you realize okay, there is some choice of m and n's that that does the job for you. Let's see. So, for example, we have m here, n here. Region. These are the allowed regions. Basically, there is a parameter space you can choose your m and n to be.
M and n is like for phi 1 and phi 2 you have different.
Yes, sorry. This guy is 1 to m, and this is n. So my group would be cubic m times cubic in groups. Okay? I would have m and plus n copies of cubic groups. So just to give you a feeling about what the parameters are, it's actually fairly large. So if you choose m to be 1, m to be 3, n needs to be bigger than and equal to 44. It's still too large.
So this is one loop, yeah?
Yeah, this is one loop. Well, if you do 2, it could improve. I hope it improves.
You want this to survive down to d equals 3, right?
Yes, yes.
So this could shift it a lot, so you might go to smaller values, go to much bigger, so.
Yes, yes.
So it could even get better, you don't know.
Let's hope for the best. Go ahead.
Can you maybe say something about the RG flows? How many are relevant?
Exactly. So if I analyze my data function lambda g, and I analyze its eigenvalue, there is one negative direction. So there will be 3 relevant operators, which is too much actually. The original ones also have it. The 3 plus 1 dimensional x types of fixed points also have at least one extra direction. So let me just summarize by saying that the current models in the market all have at least 3 relevant operators. Some of them have more. But so we want to one future direction, of course, is to see whether we can have 2 relevant operators. But I think that's see.
So the shadow region in this phase diagram is where you have
it's allowed where you have a negative sum of mass. And these regions, all the sum of masses are positive. So let me write something that is actually quite interesting. Is that lambda 1 is going to be 1/3 1 over m. We can take a limit with m over n fixed, and we take a limit at n goes to infinity. Okay, and you can solve for the beta functions easily. So interestingly, lambda 3 is equal to 1/6x 1/m. Lambda 4 is 1/3 minus 2/3x 1/m. Lambda 5 is negative 1/6 square root of x 1/m. So, okay, these are the couplings of the fixed points I was talking about. And let's look at where the order 1 things are. Okay, this is order 1, this is order 1. The rest are order 0, order 1 or n. They decay to 0 at infinity, right? So let's look at what the couplings are. Lambda 2 is this guy, okay? Lambda 4 is the one for phi 2I summation to the fourth summation over I, okay? Yeah, so what is it? It goes back to Ising model at larger limit, basically. This is an interesting fact, actually. The first type of this model, or the first type of these models were started by long ago by Victor Emery. Which is on PRB. Volume 11, 1975 to 39, okay? And he started a single copy of cubic model, okay? He realized the cubic model can be understood as like n copies of Ising model and coupled through their mass terms, and you preserve the mass deformity, preserve the cubic symmetry. Which this model is basically a larger model coupled with the double twist deformations. Okay, actually he realized there is a Fisher renormalization, which in our language is basically saying that delta phi goes to delta phi of Ising plus 1 over infractions, and delta phi squared goes to d minus delta phi squared of Ising plus order 1 over n fractions. Okay. These are usual things in large density. It's changing of boundary conditions in ADS, and you can talk about the flows like this. Okay. So the reason I'm mentioning this is because I believe our model, this phi coupling model, can also be understood as a larger limit, as a perturbation around n copies of Ising models. And there's a possibility that you can use conformal perturbation theory to analyze these fixed points directly in 2+1D. Then you would be able to write, for example, the scaling mentioned here in terms of the conformal data of the Ising model, And this first step, you treat this beta function, you solve this beta function directly into +1, and then you can analyze the renormalization of the couplings of your epsilon operators. If it has a negative contribution, you would be able to show it directly that into +1D we will have a safety that does. That's also related to what Slava was saying. I think it would be much nicer if we do 2+1D directly and get to see whether this persistent order appears or not.
I got lost a little bit there. In this diagram you brought above the line for the allowed region, the upper one. Does it go linearly at large?
Yeah, it goes linearly at large n. So I think it's 1 over 9 or 1 over 8.
So then there is some value of x that you're fixing for which you are inside the allowed region, so it should...
Yes, these are the fixed points, but if you want the sum of mass to be negative, it tells you which x you are bounded.
But for any value of x, you
still have a fixed point.
But you're going to decouple easy model.
At infinite n.
Which is, however, still inside. So this would mean that if it was like that, like in formal epsilon dimension, does it mean that decoupled easy model actually have negative terminal mass? It's not possible because of what you said before.
Well, okay, my sum of mass would be proportional to 1 over m.
The terminal mass.
Yeah.
Okay, thank you.
That's basically what's happening. Yeah, so I don't know. Yeah, okay, I already explained that I want to do directly control perturbation plus.
Officially you're out of time, so if you can.
Yeah, I just have a few more comments. First of all, as I said, there are still some things that you need to improve about these models. First of all, as Max saying, it has too much relevant operators. It has 3. But I guess at least in lattice models, it's not too hard to imagine. I remember around 2000 there was this model that people were dealing with the computation between superfluid and ferromagnetic. So they set up some lattice models and to study this, and the safety they are approaching the tetra-critical point. Okay, with 3 relevant operators, so it's tetra-critical point. We are starting with O5 Wilson Fisher safety, because the lattice model only preserves O2 times O3. Okay, and therefore, if you look at the spectrum of O5 of this subgroup, you will have 3 relevant operators you need to tune. At least they were able to reach the point. That's one thing. I think this is hard, but this is not the biggest worry I have. The biggest worry, of course, is there are too many scalar fields. Right? You have like 3 plus 44, it's around 50. And your Hilbert space would be too large if you are trying to do quantum power simulation. And so there are 3 types of reality. Field theory reality, lattice reality, and reality. We are at field theory reality at this moment. We want to push it to lattice reality. And so we would need to search for finite groups that does this kind of, that has as less number of vector models as possible. And Hugh Osborne has a paper where they brute forcefully solve this equation numerically for some lower number of scalar fields. And I was hoping that we could do it together to just add a few lines of the code to check whether the fixed point he found has negative thermal mass or not. But on Monday he told me he already did it. So there's no negative thermal masses in the setups he was finding. So the next step, I think, is we still have some chance. The next step is to actually work with finite groups. You pick a finite group and you write down Landau series for these finite groups. Actually, there are like infinite many finite groups. For finite groups of order less than 800, you would have 10 to the 7 finite groups. So this is a huge space. And we need to do a systematic search in this huge space to search for a model that does the job for us. Okay, so last comment is, okay, we also checked tetra times tetra and tetra times cubic. Nothing is new in tetra times tetrahedron times tetrahedron theory. There is a model with tetrahedron times cubic. You can find a region. There is a negative thermal mass. There were 2 other approaches I already mentioned. One is to work with long-range models into +1 dimension, and that's the approach taken by Tai, Damansky, and Smalling. So they were able to find long-range models with persistent order. The last is okay. There is another approach is 3 + 1 dimensional Banzak's type of fixed points. That approach also exists. That's all I want to see, and thank you.
So I missed something. So are you doing one loop calculation in terms of lambdas or in this model?
Yeah, okay, you just, the calculation, okay, you have a Lagrangian, right?
Yeah.
You just need to rewrite this in terms of tensors, basically in terms of this and the MIDKs.
Yeah.
And you plug this in this formula and you solve for zeros. And then you check the eigenvalues of this matrix to see whether it's negative or not. It's a really easy calculation.
I think what I'm confused is that at large M limit, the lambda 2 and lambda 4 is order 1.
Yeah.
So how do you do the perturbative calculation?
Okay, I'm missing epsilon here.
Oh, okay.
So I scaled my coupling constant with,
Ah.
divided my coupling constant with epsilon. That's more. Sorry for the confusion.
I just wanted to comment that this realization in terms of VIR of n-coupled Isings in conformal perturbation theory was actually studied by Damon in a paper of last year.
Yes, okay, I should say it. Okay, there is a paper by Zohar and Delson Duffin. They were, conformal perturbation. There's one by Dan Binder, and there's another one by, let me see it. By Jiangli Grading and Eric Hamilton. So they are, I think all these would get to the same answer for the Lagrange corrections of the critical factors.
So just to check if I understand correctly. So for example, one could in principle try also in 1+1, but I guess there
you need long range, right? You need long range
because then you would find a temperature like 1D, so not even discrete symmetry.
Yes, you need if you can play. Yes, you can play with long range models. Actually, you can play with boundary CFDs. Hopefully, you can find some examples.
Okay, that's fine.
Please don't forget that today we are